Welcome to Calculus 4.2, April 2nd class. Today we're going to do Euler's formula and Taylor series. So today I get to show you one of the coolest things in all of math. And you guys just have learned enough math to see how it works. So what you've got so far is Maclaurin series. So we did Maclaurin series in class for e to the x, and we got 1 plus x squared over 2 factorial, x cubed over 3 factorial. If you forgot how we got that, go back and look at those videos. Then in class we also did sine of x, and we found out sine of x can be expressed by this expression right here, and you get x minus x cubed over 3 factorial plus x fifth over 5 factorial, etc. The homework assignment for last class was to find the Maclaurin series for cosine of x. And if you did that already and you did it correctly, then you know that it's this. It's 1 minus x squared over 2 factorial plus x fourth over 4 factorial, etc. So one thing that's interesting to just compare these two, by the way, if you recall what an odd and even function are, sine is an odd function because its symmetry is like this. Right, this is odd symmetry, and this is even symmetry, right? So cosine looks like this, sine looks like that. Odd symmetry, even symmetry. So sine is an odd function, and look how all of the terms of the Maclaurin series have odd powers. Cosine is an even function. All of the powers of the Maclaurin series have even exponents. So that's not a coincidence. You can think about, how these even powers all do things like this. They all are symmetrical around the y-axis, and so is cosine. These odd powers all do things like this. They are anti-symmetrical about the y-axis. Here's your even ones and your odd ones. All right. So what Euler observed is that these three expansions seem to have something to do with each other. It makes sense that sine and cosine would have something to do with each other, but why would E have something to do with all of that? Well, it all comes down to one of our other famous concepts in math, which is I. I is the square root of -1. So we're not actually doing anything in calculus with complex numbers. This is just this is the only thing we're going to do with complex numbers. By the way, it's not in the AP exam. It's just something to really look at and think about. So all you need to know about I, which is the square root of -1, which you probably learned in your pre-calculus or your algebra 2, is that I to the 0 power is 1, I to the first power is I squared is -1, I cubed is -I. And then you can sort of continue a table like this. I to the fourth is back to being 1 again. I to the fifth is I to the sixth is -1. I to the seventh is -I. And it goes on like that forever. So all the powers of I can work out that way. All right, so here's how that's useful. In the Maclaurin series for e to the x, we are going to let x equal I theta. All right, so theta is just another variable, and I is your square root of -1. So we're going to do substitution into this formula. So here's what we get when we do that. You get e to the I theta equals, so 1 plus, that's the 1, and then for x we're going to put I theta. And then for x squared over 2, what I'm going to do is pull the I squared out front, and the theta squared we'll put in the top over 2 factorial. This is really just I theta squared. It was going to give you I squared theta squared. I pulled the I squared out to the front. That's this term. So your next term is going to be plus I cubed theta cubed over 3 factorial, and then it just keeps going like that. I fourth, theta fourth over 4 factorial, and then I fifth. I'm writing out a lot of these terms because we need to be able to ascertain the pattern which alternates in a strange way. I'm going to go out to the 7th power. It's theta 7th over 7 factorial. Did that all fit on the screen? Yes, it did. Okay, so now we're going to use this information to simplify what we have here. So that e to the I theta now equals the 1, I to the 1 is just I, but so we're going to take advantage of, for example, I squared is -1, so instead of plus I squared theta squared over 2 factorial, I'm just going to write minus theta squared over 2 factorial. All right, I cubed is -I, so instead of plus I cubed, I'm just going to write minus I theta cubed 3 factorial. And so I'm just going to go along substituting all of the known values for the powers of I. right? So I fourth is 1, so I have just plus 1 theta fourth over 4 factorial. I fifth is negative 1, so I'm going to have, I fifth is I, sorry. I fifth is I, so I have plus I theta fifth over 5 factorial. I sixth is negative 1, so minus theta sixth over 6 factorial. And then I seventh is negative I, so minus I theta seventh over 7 factorial. Okay, so far that doesn't look too exciting, maybe. But what we're going to do is we're going to regroup the terms. All of these go forever, right? These sums. So we're going to regroup the terms. We're going to group up the real terms and the imaginary terms of this sequence. So for my real terms, I have 1 theta minus theta squared over 2 factorial plus theta fourth over 4 factorial minus theta sixth over 6 factorial. That's all the ones that I wrote down, but it keeps going. All right, and then it's going to be plus. So I'm basically just going to separate these out. We'll do the imaginary terms now. So I have I theta, and then I have minus I theta cubed over 3 factorial, and then I have plus I theta fifth over 5 factorial, and then minus I theta seventh over 7 factorial. Yeah, so now we're going to do one more thing to these terms, which is we're going to factor the I out of this last section. So I'm going to keep this up here the same. 1 minus theta squared over 2 factorial plus theta fourth over 4 factorial minus theta sixth over 6 factorial plus etc. Down here I'm just going to factor out the I, so plus I theta minus theta cubed over 3 factorial plus theta fifth over 5 factorial minus theta seventh over 7 factorial, etc. All right. I'm laughing because ... and then I close parentheses, but the dots never end, so when did I close the parentheses? All right, so now here's the cool part, okay? This is the cool part. So see this part right here? Let's see, let me get a different color. See this part right here? That is this. So that is just cosine of theta. And then see this part right here. That is the same as this guy right here. So this is I sine of theta. So the remarkable result you get is that e to the I theta equals cosine theta I sine theta. So there's a couple of different ways that people use that. So one thing is you can multiply both sides by radius r and get r e to the I theta equals r cosine theta plus I r sine theta. Okay, why is that interesting? Because if you remember your polar coordinate studies from pre-calculus, that is the polar form of a complex number. Now, this is the one that actually has some applications. The application is in electrical engineering, specifically in alternating circuit analysis. So I tried to find a cool video on this, but a lot of it was sort of like way more engineering-y and not enough mathy. But they do definitely use this formulation. They use this formulation, r e to the I theta, to represent complex numbers. You've seen this form to represent complex numbers. You've seen a plus bi, that's the rectangular form to represent complex numbers. But electrical engineering people use r e to the I theta to represent complex numbers, and they use complex numbers a lot to represent impedance, inductance, and current and voltage in an alternating circuit. Alternating, what do you call it? Alternating current circuit? Yeah, AC circuit. So if you guys go into electrical engineering, you'll see that, by the way, electrical engineers use, instead of I for square root of negative 1, they use J for square root of negative 1. The reason that they do that is because they're already using I to stand for current. You know, like I for current. Go figure, these things have histories that no one can disentangle. Now, here's the best part, though, for pure math people like me, applied math people like this part. But I think a lot of you guys are going to like, what if we take this formula here, this one, and let theta equal pi, right? Then you will have e to the I pi equals cosine of pi plus I sine of pi. So traditionally, people usually write e to the pi I. I think it just sounds better trying to say I pi. You could say either way. But cosine of pi is 1, negative 1. And sine of pi is 0. So this is the very famous Euler formula. Some people like to write it like this: e to the pi I plus 1 equals 0. So my guess is that a group of people like you have seen this before. This is Euler's equation. It's very famous because it's a simple equation that relates the 5 most fundamental constants in all of mathematics: e, pi, I, 1, and 0. So there's a lot written about that. So you can look up Euler's equation, or sometimes people call it Euler's formula, and find lots of cool vids about how cool it is. But that is it. I bet you've seen it before. And now you, unlike most people who have even seen this, you know where it comes from, and you can show somebody where it comes from. Okay, next up, we're going to do Taylor series.